I am Swetha Thammisetty, Assistant Professor, Department of Data Science, MITS. Today I am going to discuss about AVL trees in data structures. So, see here, it is having some definition like AVL trees is a self-balanced binary search tree. That means an AVL tree is also binary search tree, but it is a balanced tree. A binary tree is said to be balanced if the difference between the height of left subtree and the right subtree of every node in the tree is either -1, 0 or +1. In other words, a binary tree is said to be balanced if for every node height of its children difference by the utmost of 1. In an AVL tree, every node maintains a extra information known as balance factor. Here, in AVL trees, it is one of a binary search tree, and here it is having a balance factor. It is a very important to balance a tree. And next, here it is an AVL tree is defined as follows. Like already we know that AVL tree is a balanced binary search tree. In an AVL tree, binary factor of every node is either -1, 0 or +1. Not it should be less than or greater than 2. And balance factor of a node is difference between the height of left subtree and height of right subtree of the both nodes. The balance factor of the node is calculated either height of left subtree minus height of right subtree. So, or it may be height of right subtree or height of left subtree. In the following explanation, we are calculating as follows. Balance factor is equal to height of left subtree minus height of right subtree. And see here, it is an example of a AVL tree. Here we can able to see 0, -1 and 1 as a balance factor. See, this is a perfect AVL tree. So here it is having some, I will show you something. See here. So this is a height actually 0, 1, 2 and 3, level 3. And here it is having, so here it is having a left side is 0, 0 -1, here it is -1, and here it is, this is a main node or root node. So here it is a, here it is a level 2 and here is only 1. So 2 minus 1, here it is 1. And see here it is having a 1, 2, 3. 3 minus 3, here it is 0. And coming to here, it is 0, like here it is 2 minus 2, so it is 0. Here you can see here 1 minus 0, so here it is 1. So taking here 1 minus 1, it is 0. So likewise, we need to calculate the binaries, AVL tree balance factor. And next one is AVL tree performing every operation like insertion, deletion. We need to check the balance factor of every node in the tree. Whenever we are inserting a new node in a AVL tree, we need to check the balance factor when it is balanced or not. If every node satisfied the balance factor condition, then we conclude the operation. Otherwise, we must make it balanced. We use rotation operations to make the tree balanced. Whenever the tree becomes imbalanced due to any operation like insertion, deleting, we need to balance the tree. Rotation operations are used to make a tree balanced. And rotation is the process of moving the nodes to either left or right to make the tree balanced. And see here are the 4 rotations like different rotations like single rotations and double rotations. These are the 4 rotations. And coming to the single rotation, here LL rotation and RR rotation are the 2 types of rotations. These 2 comes under single rotation. And this is a double rotation, like left right rotation and right left rotation. So these are a double rotations. These are the 4 types of rotations in AVL trees. So if we are having any left rotation, means we take left only LL rotation, and only our right rotation means we go for RR rotation. If it is having some right and left subtrees or imbalanced, it means we go for LR and RL rotations. These are all comes under different rotations. We need to use these rotations for balancing every tree. Next one here, LL rotation. This is a first rotation in single left rotation. LL rotation, every node moves one position to the left from the current position. To understand LL rotation, this is the example. See here, for example, we can insert 1, 2, 3. So first we insert 1, and then see here it is a binary search tree. So we need to check the properties of binary search tree also. So then 2 is less than 1, sorry, greater than 1. So then we need to go right side, and again 3. So then here the balance factor is, so 0 minus 2, so this is minus 2, and see here 1, 0 minus 1, so this is minus 1. So here it is a loss level, so this is a 0. So this is imbalanced because of this having a minus 2. The property is having only minus 1, 1 or 0. Either we need to balance with 3 numbers only. So here it is showing minus 2. Then we need to do some rotation and we need to balance the tree. So here it is having a left side, so all the things are in a one screed, no, right. So then we need to check left rotations. So to make the balance, we use left rotations when moving the nodes position. So we can rotate the tree in 2 left positions. So see here, see 3 goes to up and 2 is the root node, and 2 comes to the left of 2. So this is the resultant of LL rotation. So here the check the balance factor 0, 0, 0. So all the ways it is satisfied the AVL tree. So this is the LL rotation. And next one is here, it is a one of the RR notation comes under single right rotation. So here insert the same 3 to 1 in a sequence. So then it is a tree is imbalanced, like here the height of the tree is 2. So then we need to rotate the tree in a right way. So then here it comes to the right part and these two comes to the right part, then the tree will look like RR rotation completion. So here the balance factor is satisfied. So this is the single right rotation. And next one is, this is a RL rotation. That means left right notation. Whenever the tree is imbalanced, like the LR rotation is combination of single left rotation followed by the single right rotation. So LR means here left and right. First we need to check left side, and after that we have to go for right side. So this is a combination of single left rotation and the single right rotation. In LR rotation, first ever node moves one position to the left, then one position to the right from the current position. To understand LR notation, this is an example. So whenever the tree is in this combination, like left and right, then we need to do first LL rotation. So left rotation, then the tree will be taken place like this. So after completion of the LL rotation, for this one we need to take again the right rotation, right rotation. Then the tree resultant will be like this. So this is the example for the LR rotation. LR rotation means first we need to check left side, after that we go for the right side. Let's see here, Right left rotation, this is the last rotation. So here this is a combination of both single right rotation followed by the single left rotation. In LR rotation, first every node moves one position to the right and then one position to the left from the current position. To understand RL rotation, this is the example insertion of AVL trees. First we need to insert 1, then insert 3 and then insert 2 by using binary search properties. And then see here, it is a -2. This is an imbalance factor. So we need to balance the levels. So first we need to take RR rotation because this is a right side. So we need to take right side. So then if we rotate it in a right side, it will be moving like this. And then after completion of the RR rotation, we go for the LL rotation. So after completion of the LL rotation, then the balance factor is satisfied. So this is a RL rotation. Next, in AVL trees, there are some operations like searching, inserting, and deletion. So searching is like whenever we want to search an element, we can go for searching whether this element is find or not. Likewise, we can search the structure. And coming to the insertion, we can insert the element, and we can every time of a insertion we need to check the balance factor of every node what we are inserting. And after deleting, so whenever we are deleting, the balance factor is adjusted or not, we need to check. So this is the additional factor in AVL trees. Next one, these are the searching operation in AVL tree. So steps for searching element. So in AVL trees, the search operation is performed with order of log n time complexity. The search operation is performed similarly to binary search tree only. We use the following steps for searching an element in AVL trees. Step 1. Read the searching element from the user and compare the search element with the value of the root node in the tree. If both are matching, then display given node is found like that and terminate the function. If both are not matching, then check whether search element is similar or greater than the node value. If search element is smaller, then continue the search process in left subtree. After, if search element is larger, then continue the search process in right subtree. Repeat the same until we found exact element or we complete when the leaf nodes. If we reach the node with the search value, then display element is found and terminate the function. If we reach a leaf node and the element is not matched, then display element is not found and terminate the function. This is like normal binary search tree properties for searching an element in AVL trees. And for insertion and deletion, it is different to binary search tree. So in AVL trees, the insertion operation is performed with order of log n time complexity in AVL tree. The node is always inserted as a leaf node. The insertion operation is performed as follows. Insertion of a new element into tree using binary search tree insertion logic only. After insertion, check the balance factor of every node. If the balance factor is greater than 2 or less than 2 minus 2, then we need to check the balance factor. If the balance factor of every node is 0 or 1 or minus 1, then go for the next operation. If the balance factor of every node is other than 0 or minus 1 or 1, then we need to check the imbalance. So we then perform the stable rotations by using single rotations or double rotations and go for the next operations. So this is the one of the example. Here I am going to insert the values from 1 to 0 sequentially. Then the tree will looks like, see, first I am going to insert 0 here. 1 here. Tree is balanced. then 1 minus, 0 minus 0, it is 0. So the balance factor of 1 is 0. And insertion of 2, whenever I am going to insertion of a number 2, 2 is greater than 1, so I have to insert it a right side. So 0 minus 1, this is minus 1, so balance factor is correct. And insertion of a 3 value, see here, 3 inserted in a right side of 2, then the balance factor of root node is minus 2. So the property is like we need to satisfy the balance factor either 0, minus 1 or 1. So here it is 3 is imbalanced. So we need to take LL rotation. So this is all in a right side. So we have to take LL rotation, then the 3 will balance it. So after rotating of a left, then it shows the 2, 1, 3. The balance factor of all the things are 0, like 0 minus 0, 0 and 0 minus 0, 0. Here it is having a 1 minus 1, 0. So the balance factor is balanced. And next, insertion of a 4. Here I am inserting number 4. So after insertion of a 3, so immediately we need to insert 4 after the 3. So 3 is like balanced. So because of all balance factors are minus 1 and 0 only. So after that, insertion of 5. So insertion of 5 means, see, 4 after 5. So here the balance factor is changed like minus 2 and minus 2 for the 2 and 3 values. So here first the balance factor we need to check here. So because of first we need to check this minus 2, after we need to balance the 3, then if it is not changed here means we go for here. So first we need to take this part of 3 and then we need to take LL rotation. So after completion of the LL rotation, the balance factors are balanced. So you see here it is not minus 2, it is minus 1. So the balance factor is satisfied. So after completion of the operation only, we need to insert a new element. So after completion of the rotation, after completion of the balancing factors, then we need to insert the element like insertion 6. So after inserting a 6, the balance factor of root node will be changing like minus 2. So see here, it is very important and very typical to rotate the tree. Here root node will be a imbalanced. So we need to check like this is a left side and this is a right side and this is a left side of the tree. So first we need to check this part and then balancing with the left rotation. So these are all skewed to the right side, so we need to do left rotations. So here 4 is the root node. After completion of the rotations, 4 is a root node and the tree will be changed like this. Okay, this children will be taken place to the 2 children. To root node of a 2, the 3 will be a children, and the balance factor of both AVL tree balance factors and binary search tree properties are satisfied. So then after insertion of 6, so insertion of 7. So after inserting of a 7, there is a change in root node 5. So root node maybe leaf node of 4, it is a 5. So after this is in a right side, so we need to change the from here to here, we need to change the balance factor. So then rotate the tree into left subtree, then the tree will be changed like this. 6 will be the root node and 5 and 7 be the children for that. And insertion of 8. So after inserting of a 8, there is no change in a balance factors. So tree is balanced and satisfying the binary search tree properties also. So this is the completion of insertion of all the nodes from 1 to 8. If we are deleting any node, say this is an insertion example. If we are deleting any node, same way we need to delete 8 and we have to check the balance factor of every node. And after completion of 8 deletion, we go for the 7 deletion, or it may be whatever the element we are deleting, we can delete and we can check the balance factor of every node. Then it is either 0, -1, 1 only. If it is greater than -1 or greater than +1, then we need to change the balance factors. So likewise, we need to do some searching operations, deletion operations, and insertion operations. The main factor is here. We need to check the balance factor. For every node, we need to check the balance factor and satisfying the binary search tree properties. So that's the thing we have. And next here, deletion. So already we know how to delete. So in AVL trees, the deletion operation is similar to deletion operations in binary search tree. But after every deletion operation, we need to check whether balance factor is satisfied or not. If the balance factor is after deletion, then go for the next operation. Otherwise, perform the suitable rotations to make the tree balanced. So, an arguments for AVL trees are like search is order of log n, since AVL tree are always balanced. Insertion and deletion are also order of log n. The height of balancing elements no more than a constant factor to the speed of insertion. Arguments against using AVL trees are it may be disadvantages by using AVL trees. Difficult to program and debug, more space for balance factor. Asymptotically, it is a faster, but the rebalancing at cost maybe take some time. Most large searches are done in database system on disk and use other structures like B trees also. Next one is here the time complexities of insertion, deletion, and searching of a AVL trees. See here, insertion of a unsorted means order of 1, and deletion order of n, and searching order of n. For binary search tree, insertion is order of h, deletion order of h, and searching order of h. Balanced binary search, that means AVL tree, insertion order of log n, deletion order of log n, and search order of log n. So it takes some time to complete the operations because of that balance factor. So, and thank you. Thank you for giving this opportunity. Thank you very much.